Good evening, everybody, and welcome to OpenMinds, the Open University series of public talks. I see we have gathered an excellent audience here tonight. Clearly many are you people, but also many participants from elsewhere in education and from industry. My name is Professor Anne de Rook. I'm a professor in computing at the Open University, and I'm delighted to have you with us tonight for our talk, Performing Online Live Experiments 24/7, an Internet of Laboratory Things. With this session, we hope to introduce you to and enthuse you about our new open STEM laboratories. This is a major 5.4 million initiative, 50% funded by the Higher Education Funding Council for England, also known as HEFCE, developing remote and robotic access to various experiments for students, both within the Open University and at other institutions. The Open STEM Laboratory builds on the great success of the Open Science Laboratories, funded amongst others by the Wolfson Trust, and it represents a new vital step in the OU's mission to educate more science, technology, engineering and mathematics graduates. I've had the privilege of being involved at the start of the Open STEM Labs, which blossomed as the next phase of the Open Science Labs, and as the largest academic institution in the UK, and a world leader in flexible distance learning, the OU is very committed to leading online innovations in how we deliver our teaching and support our students, and this is a prime example. As you can imagine, teaching practical engineering and laboratory skills is a challenge in a distance teaching environment, and the STEM faculty in particular has worked through many generations of solutions to this challenge, for instance through residential schools, which are one way of doing that, but also what we call shipping kit, i.e. this kind of thing, and also this kind of thing that you would then have to find a place for in your home that's far removed from your dog, for instance. So, over the last decade or so, we have taken a radically innovative approach made possible by improvements in access to broadband and the internet, a journey leading to today, where we can support science and engineering students in operating remote experiments 24/7 in our new Open STEM labs. One particular message I want to emphasize: yes, this facility builds, as I said, on increased availability of internet bandwidth, but also in a very large measure on the excellent research, imagination and foresight of our academic community, as well as our research infrastructure, not just in the subjects we teach through the labs and their pedagogy, but also through our leading-edge expertise in novel technologies and methodologies that support the lab's delivery, such as networking, interaction design, and virtual reality, just to name but three. This facility celebrates excellence in the university's diverse research portfolio, as well as excellence in our leadership in teaching, and it could not exist without both of those elements. This evening you will hear from 4 OU academics who are working in this project and have moved it along. Professor Nick Braithwaite, OU Professor of Engineering Physics, will introduce the concept of the Open STEM Labs, which will in effect form an Internet of Laboratory Things that could be open all hours and available in a real distance learning setting. After Nick, Dr. Mark Hurst, Senior Lecturer in Biology, who leads the Open Science Laboratory, will explore how materials analysis can be conducted from afar through keyboards and screens. Then, Dr. Ulrich Kolb, Senior Lecturer, School of Physical Sciences, who established the faculty's first robotically controlled telescope, Pirate, in 2008, will share the thrill of real-time observing of the night sky and how to do it collaboratively and without co-location. And finally, Dr. Tim Drysdale, Senior Lecturer in Electronics and Academic Lead for the new 2.7 million Open Engineering Lab, will describe how practical STEM works at a distance now that the equipment no longer needs to be in the same room as the student or the educator. He will conclude with some examples of an Internet of Laboratory Things working in practice. Then our speakers will form a panel chaired by Lucian Hudson, Director of Communications, and those of you in the room will have an opportunity to ask them questions or comment on what they have said, and we will also take questions from social media. Tonight's event will end at 7:30 p.m. with closing by Professor Simon Kelly, Interim Executive Dean for STEM, after which we invite you to join us for drinks and to interact with our robots and demonstrations in the foyer. And now for the first talk, Professor Nick Braithwaite.
Thank you for those introductory remarks, which sets the scene very nicely. OpenMinds performing online experiments 24/7. I'll say something about 24/7. I mean, we are going to tell you how we're available in principle. The apparatus that we're talking about will be available 24/7, but we are still restricted by the Earth. So when we're talking about astronomy and so on, you've got to wait until it's dark where the telescope is. So some things are constrained. But let me tell you first about the Internet of Laboratory Things, which is a strapline that we have developed over the duration of this project. I looked up in that well-known source which all academics go to when they first want to explore a subject, Wikipedia. Actually, it's not bad. I pay money to them to improve, so let's keep them going. The Internet of Laboratory Things wasn't there, but the Internet of Things was. And I found that actually, if we just highlight what's in the Internet of Things, then we've got a description of what it is that we're going to do, what we are doing. Smart devices, embedded sensors, actuators, network connectivity to collect and exchange data. That is meat and drink to a scientist and to an engineer and to a technologist and to a mathematician. So it's STEM. We're very inclusive. Now, let me ask you this. I'll tell you the answer in a minute. What do you call a space for active learning in science, technology, engineering, and mathematics? Well, before we answer it, of course, we're academics, there's a caveat. It's got to be open to people, places, methods, and ideas. It's got to be available outside office hours. It's got to be inclusive. It's got to be as accessible as the rest of what the Open University does, because that's what we do. And it has to provide an authentic interface to real data. Those are the criteria that are set down. And so what do we call it? We call it the Open STEM Labs. I'm pleased of the opportunity to explain this because it's a concept that's been clear in my mind for some time, but in conversations with people, when they start to glaze over, I realize that it would be much easier if we just had a building. Then we could explain it better. So imagine the Open STEM Labs as a building. This is the space in which we're going to do our laboratory work, or our observatory work. And within that building, there are different regions. There is the zone called the Open Science Laboratory. And many building projects, you build one bit first, and then you save up, you get more money and build the rest of it. We built that bit first, courtesy of the Wolfson Foundation. And then, thanks to HEFKI, we've been able to add 2 new wings, the Open Science Observatories. We were doing some of that already in the Open STEM Lab, the Open Science Lab, now we're doing a bit more. And then the Open Engineering Laboratory, we weren't really addressing that part of the curriculum, and it's fantastic that we're now able to do it. So we put our team together, we got our bid together, and we got the resources. And why have we done it? What do I want you to go away thinking? This is the reason why they did it. I've got it down to just 6 bullet points. Of course, when you make a bid, it's 6 pages, but this is a distillation of it. So I'm just going to pick these things out to remind you why we're doing it. We want authentic online practical work in labs and observatories for our students. We have an obligation to provide that, and we have an enthusiasm to provide it. We want access to tools of professional science and engineering, and we want collaborative learning environments. That's what being in a lab, being at an observatory encompasses. And then we want a place where we can do pedagogic research into active STEM learning. This is active learning that we're going to be witnessing, and we want to make it better for seeing it happen. We want teaching collaborations with other educators outside the OU. And once we've got it on the wire, it doesn't matter where that other institution is. And we want engagements between researchers, teachers, and students. And we're able to do that because we've got the kind of equipment that researchers like tinkering with, like playing with, and like showing off. So I think we have the right elements to it. So much so that my boast is what it says at the bottom of that slide there, the online open STEM labs, practically better than the real thing, because we have all these other affordances around it, particularly the collaborative working, the collaboration across institutions, across the planet. That's how it works. There's our laboratory building, the Open STEM Labs, and here are students sitting in their garrets with their Wi-Fi hubs. And from there, I want to tell you more about the details. So Mark Hurst, if you would come up here and join me and take us on. Mark is the director of the Open Science Laboratory part of it.
Thank you, Nick. Good evening, everyone. Good evening, everyone at home. I'm going to kick off tonight's proceedings by starting about the centre of the picture Nick just showed, which was the Open Science Laboratory. This is an online portal that's become rather a mainstay in our science teaching over the last few years. And it's added to that depth and to the blended learning that our students have been used to. It has about 100 different types of activities in it. And in fact, it's not just there for OU students, it's open to the public as well. 48 of these activities are open to the general public to use, to schools, to teachers. It consists of a range of different types of experimental activities that allow students to go in and collect data, write reports, make experimental choices, make observations. Some of these are remote. A lot of them are through what we call interactive screen experiments. So these evolved from the types of experiments that were originally mailed out on DVDs and CDs to students that they would do at home on their own computers. These are now done through little apps that run through the Open Science Lab. And to add to that, to allow our students to analyse and prepare data for their reports, we provide a whole series of data analysis tools. It's very difficult in a few minutes to give you a flavour. Put an Open Science Lab into Google if you've never been there, register, and you can take a look yourself. I can only explain a few things. I'm going to give you a very brief flavour of the type of activities our students do in the Open Science Lab, because I want to actually then show you where we're going next in terms of actually integrating real live analytical instruments. Just at the bottom is a reminder that to show how mainstream the Open Science Lab has becoming our teaching, that this year we have about 50,000 student hours of activity using the Open Science Labs in the various areas of science curriculum. So if you go to the Open Science Lab, it looks like a series of tiles or apps. I've just picked out 6 as examples. One of the very first ones that was developed originally as a mail-out tool was a digital microscope. This has proved incredibly valuable for teaching all aspects of geosciences, of environmental sciences, and in my field, in biology particularly. It's an incredibly valuable tool because you can put authentic images there, whole scans of slides, and allow students to actually choose how they collect their data, what they present, how they score, how they record it. So it's a great tool for teaching practical science. We have analytical instruments. For example, the DNA Quantitation Lab is effectively an online spectrophotometer programmed with a whole range of spectrophometric data for nucleic acids, which again allows students to go in. It allows them to make mistakes. They can put in the wrong parameters and actually make errors. And so those types of authentic data actually lend an element of real practical exploration for students. We also have another example here used by level 1 students called a spirometer, where students, it's actually based upon a data set based upon human epidemiology studies. Again, it allows students to propose hypotheses, go in and collect data that's based upon real human physiology data sets. So these are just 6 of the types of apps that sit in the Open Science Lab. Some of them also have much more immersive environments, making use of Unity programming, where exploring a space is important, like field trips, or walking around a laboratory to find a pH meter or some solutions to do some laboratory chemistry. But it's not all about students collecting data from our labs. It's also about people out there doing citizen science, actually putting data into apps. The first of which was the iSpot, where people put in biological data. Many hundreds of thousands of data sets have been collected. Our students also use this in various modules. And Treezilla, which is a record of trees around the world. So it's not just about our students going in there and carrying out science. It's about a wider outreach to the general public, engaging them, bringing into our OU resources into the Open Science Lab to carry out science. So that's a very, very quick trip around what the Open Science Lab represents. As Nick's just shown you, those are like peering through the window of a laboratory, where we've got students, we've allowed them in to have a little peek, but actually now what we're going to do is actually try and open the door and ask them actually through. And I'm going to give you a couple of examples of real live remote analytical instruments that will be appearing in the Open Science Lab in the next few years. So for example, these are online optical microscopes. So whereas a digital microscope presents a static image, which is incredibly useful for teaching the basics of microscopy and exploration and data collection, An optical microscope allows you to move things around. It allows you to look at things that are wiggling around and moving around, like worms in genetic experiments. So it takes that experience to a new level of interaction and authenticity. There's a whole range of desktop instrumentation, for example, to do genetic analysis with quantitative polymerase chain reaction, or an online real-time access version of the DNA quantitation instrument. One of the great advantages as an instructor that these give me is that whereas a piece of a programmed application is sat there, it's very difficult for me to update it. I can go with one of these remote instruments and change a sample overnight. I can be reactive to my students, which means it's a more robust teaching tool. So I can use these instruments much more interactively as a teacher. So for me and my colleagues, it's a very valuable tool I can use. There are also much more larger instruments, for example, a large flow chemistry system, and this monster, this gas chromatography mass spectrometry system. But I'm going to give you a very quick view of what life's like with an electron microscope, and if I can remember how to use, this is an example of a live view of what electron microscope. Some of you here in the hall may have actually been using this outside, and when I was introduced, I was meant to be talking about materials. Well, this is actually, I asked you to guess, it's a biomaterial, and one thing I always find about these types of live, a quick exploration, this is a live view of an electron microscope that's sat about 200 meters behind me in one of the old BBC studios, through about 5 walls this way. This is a live view of the inside of that instrument. And these are web-based instruments that are not just remote desktops. So this is not remote desktoping to the interface that controls the microscope. We have a fantastic team of programmers who've designed web interfaces, which means they work across platforms. They can work on phones, they can work on tablets, they can work anywhere in the world. Nick's famous for having tweeted a photo from 30,000 feet somewhere over Central Asia. We've also been testing it. I accessed the instruments from Death Valley last summer just to show you can actually do it. So this is a very close-up view. If I scroll down slightly, you can see the scale bar right at the bottom. 10 micrometer scale bar, for those sat at the front can actually see it. This looks like some horrendous material, but I'm actually now going to zoom out just to show this is a live image. As a biologist, I find nothing excites a crowd more than something that's a creepy crawly. This is actually the front end of a rice weevil. Probably don't encounter them much these days, but if you came face to face with it at that power, you'd probably be quite scared. So the interface that's been designed for, in this case, relatively simple control. We can change focus, we can collect levels, and more importantly, if I capture an image, that image is stored on my computer and it can be used in student reports. So as an opportunity to present students with even a simple opportunity to see something that excites them, like a creepy crawly up close, is an absolutely fantastic opportunity. Of course, there are far more scientific and important opportunities. So that's a quick trip around the scanning electron microscope. It's sat outside in the mezzanine, outside for those people here who'd like to have a go. And we've got several of my colleagues will give you a guided tour of lots of other different creepy crawlies and things. So where do we see these being used? Tonight is also about the space science and technology masters that's about to start. The analytical instruments I've been talking about will find their first home in the curriculum in this module. For example, students will be using the light microscope and the scanning electron microscope to look at things like micrometeorite damage on the surface of satellites and things like that. And I think you can also have a look at the Mars rover and the satellites down outside. So I'm going to sum up now. It's always been mentioned, mailing out kits was what the OU started with. Here's a view of them assembling a science kit with a little microscope being used in the background. But it used to be that the only way we could show our students complicated, large and expensive analytical instruments, for example, transmission electron microscope shown here, was on broadcast TV or through video instruments. Now we can do that. We can open that door. The students can come in and actually sit in front and operate real instruments. So the next few years, these will be being integrated into the Open Science Lab and will find their way into various aspects of our curriculum. I think my time's up. I'm going to finish there. I think I should just say we are going to take questions at the end as we're all together. So it only remains for me to introduce Ulrich.
Thank you. And good evening, everyone. We turn our attention now to the heavens above. I'm talking about the Open Science Observatories, and I'm pleased to say that this initiative is resting on the shoulders of giants in a sense, if you like, because we are fortunate enough to have the pioneering Bradford Robotic Telescope now under our wings here, which we bought, and we have the experience of our own Pathfinder Pirate Telescope, which was situated in Mallorca for quite a number of years. And we have now combined these two to transform the opportunity for our students and our researchers as far as research and teaching of observational astronomy is concerned. The Open Science Observatories are chiefly concerned with the objects in the sky. The night sky, the sky above, is the laboratory for the astrophysicist. And the radiation we receive from distant sources is what we need to investigate and analyze to understand what they are made up of. So to unravel the mysteries of the universe, we need to collect photons and radiation from out there. The Open Science Observatories do this in two different wave bands. We have, in fact, you may have seen this when you came onto campus, if you're here in person tonight, near to the entrance, the main entrance of campus, a radio dish, so we can observe in the radio band. This is available for our students for remote control to investigate the structure of the Milky Way. Tonight, though, I would like to focus on the more traditional astronomy, the optical wave band, and our telescopes and observatories we use for students and researchers. They are called Pirate and Coast, and they are, as I indicated, at a very special site in Tenerife. This is one of the best observing sites in the Northern Hemisphere. We are fortunate enough to be able to place our facilities. The two here, the larger one is a 4.5 meter dome, the smaller one a 3.5 meter dome, at the area of the observatory, Observatorio del Teide in Tenerife, 2,400 meters above sea level, normally above the clouds, and it affords perfect viewing conditions for 80% of the time throughout the year. Of course, we have to wait for night to come upon us, and so I would ask for the lights to be dimmed. What we are observing here is a time-lapse of essentially a night's work of these facilities, interrupted by some local technicians and OU staff, because this was in the commissioning phase. These facilities are just up and running now for a few months, and student use, research use, would be completely via the distance. We would control and operate via the internet, and no one would mill about as would be seen in this time lapse. There's two different access modes to these observatories, which I wrote there in real time, which is the preferred option to teach the ins and outs of observational astronomy and of science in the laboratory, as far as an astronomer is concerned, by being able to send the telescope to do certain imaging tasks and then immediately investigate the quality of the image and react to it and learn from it. Or, once you're an experienced observer, you feed into a queue for a nightly program which is made up in advance, and the telescope just does it on its own. We offer both opportunities. The astronomy we do is called time domain astronomy, because what these telescopes are after is trying to see if any of these sources in the night sky change with time, and this is then driven by physics in these sources, and this is where we can learn about the science of the universe. We move on and probably want the light back up. The observatory by day looks like this. You can see the volcano in the background. You can see all the movement there of opening the dome and moving the telescope is something that students could also initiate on their own. And in the corner we see the interface, which I'm hoping to be able to show you live. And I go for this to the web browser in the same way as we had before. This is a view of the observatory just now. and it is a webcam view. So this is in Tenerife, with the dome open and the telescope staring towards the essentially zenith, because it takes what we call calibration frames. You can see here the open dome taking these calibration frames. Clouds are sort of everywhere a bit, but it is clear enough to do. I can turn on the sound. We hear the wind in Tenerife up the mountain. It really is very windy. Okay. It is this interactive device and dashboard which allows the feeling of being on site for student use. I return now to my presentation and would like to tell you a little bit about how do we use this. What kind of work do we ask our students to do, and what kind of work do researchers do? There is currently the flagship satellite by ESA, the European Space Agency, in orbit, called Gaia. It is a mission which is tasked with mapping the stars in the Milky Way with a precision which is unprecedented. This is essentially scanning the sky, as indicated in this graphic, and creating a map. This is a map, a very recent publication of a map of this satellite. By scanning the sky, it returns to the same position on the sky again and again and again, and therefore is able to pick up if anything has changed. If anything has changed, if a star, an object, changed its flux, it issues an alert down to Earth, and telescopes pick the alert up, including ours. We pick it up and swing our telescope into action and follow the source which changed over time to help the satellite in a task which it can't achieve on its own. This is an example, a very recent example, over the commissioning period of the observatories. It spans about 2 or 3 months and shows the light curve, as we call it, so the brightness of this otherwise rather boring star suddenly jumped by a factor of 10, went down, and then jumped again, as you can see in this double-peaked feature. This is pirate data obtained by, in this case, PhD students on campus. If you combine this data with data by other telescopes around the globe, the network following up Gaia sources, it looks even more complicated, this double spike. You may ask, what is going on? This is not a star. What does it do? What we see and observe is general relativity. Light is being bent by gravity, and this is just explaining what happens. We see from Earth a star, which is rather boring to begin with, doesn't change. Then a second star crosses the line of sight. We don't see the second star, but we see the second star change the way the light is traveling, and therefore bent, and this magnifies the background star and makes it brighter. And then when our traveling star is gone, it goes back to what it was before. The complicated structure we see here means it's not just a star, it is a double star, a binary star, producing this. And by looking at the signal, we can learn something about the makeup of this traveling star. This is exactly what we will enable our students to do in the now started MSc in Space Science and Technology. The very first module of this is in space science. It's based around case studies. It involves very famous missions, Apollo 11, Gaia, as I mentioned, Rosetta, and Mars, the Mars Curiosity rover. In the Gaia case study, the students would do exactly as I just indicated here. They receive an alert by this mission, by Gaia. They follow it up with the robotic telescopes. They analyze the data, and they send feedback to the network. So they contribute to a research effort. This is just one example of how the Open Science Observatories will be used. They are encapsulating authentic research in its truest sense. We send our users, including undergraduate students, we equip them with professional-grade astronomical instrumentation and send them on tasks which will contribute to astrophysical research, embedded in wider projects. It is very motivational learning because the students, when they do this, they start in real-time mode. They are linked via audio channels while they do so. So in small groups, they discuss and debate the optimum strategy for observing and getting this job done. while they control the telescope, as I indicated. We use it also as a very effective tool in public engagement, such as now or afterwards, and I would like to invite you to the stand where you hopefully can press a button to see how you can make the telescope do what you want it to do. And with this, I would just want to stop to say our next step on this journey is to open this service up again to the public by offering a subscription service via the telescope.org website. This will widely increase the reach of the telescope and widen the audience. I'll stop here.
Good evening and welcome to the engineering portion of this evening's event. Now, by engineering, I mean that pursuit in which people creatively conjure up a vision for the world in the future. And then they don't stop there. They go about making it real. And the way that is now is the real world is a connected world with many beautiful and wonderful engineering and science artifacts in it. We have seen two of them already. We can stare to the far reaches of other galaxies, and we can peer down so that things like insects look like monsters. But the technology that connects them is electronics. The thing that makes them connected is electronics. And so we have decided to connect electronics into our engineering qualification. And that starts in October. But the interesting thing about electronics is it doesn't just connect equipment, it also connects people. And that's a very important thing if you live on the opposite side of the world to your family, for example. And also very handy if you're developing remote labs. But the critical question that arose at this point in our minds was, if the real world is a connected world, how do you go about preparing an engineer for that connected world when we have a history, and a proper and right history, of thousands of years of poking and prodding at things that are in the same room as you? But that's not the world that we face anymore. You can do more, you can be more effective if you can control things remotely. So we started thinking about what type of equipment we might want our students to interact with and where that equipment might be and where might they be. And so we have some examples that we considered for the sake of hypothetical analysis. And one of them is this amazing dance, a ballet of robots at the Oxford factory. I believe this is the Oxford factory. And in this case, the equipment is quite close to the operators, but the operators are staying well back because those orange arms go awfully fast. At the other end of the spectrum, you can put something so far away in space that you couldn't go near it even if you wanted to. So what's right for us? I think it comes down to reaction time. And the critical thing here is we're human, and humans do all of this technology to do things that help humans, and the human timescale is how quickly we can react to something. So as this person is giving away by the look on their face, they haven't done particularly well at this reaction test. But the point is that if you take a friend and they hold a ruler and then they drop it and you, with your fingers at the start of the ruler, grab it, not a much time goes by, but certainly a finite amount. And the effect of that reaction time is that anything that happens quicker than your reaction time is effectively free to you in terms of energy consumption. And this is a point that Nobel Prize winner Daniel Kahneman made in several of his works. This book, if you can get it, is a maiden Christmas reading, but it will take you more than one Christmas. In it, he did a test. To conceive of this was brilliant. Sweeties and quizzes. And with that, managed to prove that if you make someone remember something for a short period of time, they are burning real, genuine energy. And if you've got someone who's busy, like an OU student or an engineer, and you are making them burn real, genuine energy, waiting for your remote lab experiment to work, then you're not doing the best job by them that you could. So the human reaction time sets a limit on how far away our equipment can be. But how far away is that? The answer comes from the light that we use to transmit information around the world. Now, we've all heard of things like the Iron Age and the Bronze Age and the Stone Age. There is a view that we're in the Glass Age, because it's glass that carries that light around the world. And if that light was not carried around the world, we would not be in a connected world. We would not have the lives that we have now. So it's that light traveling around the world that we need to understand. So the next question is, what is the speed of light? And indeed it is fast, but it is not infinitely fast. If I was to drop something onto this desk, and at the same time send a photon firing sideways around the world, imagining there were no buildings, the surprising thing is that that photon would get back to this desk having gone 40,000 kilometers around the world before the item hit the desk. And it turns out that that distance is around about the same distance the ruler is going to drop in that reaction test. Through some complete quirk of physics and cosmological constants and human biology, it turns out that the exact right distance to put equipment for doing remote labs, where people don't have to burn real genuine energy waiting for stuff to happen, is anywhere on Earth. It doesn't matter. So with that, I started connecting things up to the internet, and it turns out, believe it or not, that the slowest part of the whole procedure is taking good old ordinary photons that are jostling about in our lab and getting them through the camera, through the computer, and onto the network cable. Once we've done that, the speed of light takes over, and it really doesn't matter. So the trick to making the remote labs work for engineering was getting the light through the camera and onto the network cable. And that's where those video calls came in before. That's what I decided we would use. So I have a small video coming up, but before I do that, I should point out that we actually have stuff littered all over campus, and on the engineering side, we are going to have something like 11 of these racks in one room, and that's just the start of it. So we're going to be doing lots of things in parallel. But that's possible because it's a connected world. Lots of things are connected. That's fine. So I was in a coffee shop in Austin, and I decided I would check the pendulum that was in my house in Milton Keynes while I was doing some development work last year. And this is just a screenshot I took. So if you look at the bottom left of the screen, you'll see a sort of a red circle. And as I was moving things and that little green arrow at the bottom, the pendulum was responding rather quickly. And in fact, I swear that pendulum looked better from a coffee shop in the east side of Austin, than it has sometimes from other places in Milton Keynes. It's really, really just outrageously good. So I'm just play it one more time. Just keep an eye on that little green dial at the bottom left there. If this will... There we go. As I move it, look at that. That is going all the way across the Atlantic, the control is, and then the camera is picking up what the pendulum is doing and bringing that information all the way back to the coffee shop. And that is right at that human reaction time. So now I'm going to do something incredibly brave, because I've connected to the system live in front of audiences from the other side of Austin. We've done it, we sent someone out to China and gave them the job of presenting the pendulum at a distance. That worked. This is done in Singapore, Hong Kong, New Zealand. And now I'm going to try and connect from about 2 feet away. Vaguely stressful. So there we go. There's the web. Right, there's a pendulum app. Now that is a pendulum sitting in my lab, and now I will do the same thing I did before. I'm going to move that green thing, and there it is wiggling away. So you might ask, what is a pendulum doing on an electronics course? The reason a pendulum is on an electronics course is because it's in a general engineering degree. And in a general engineering degree, to suddenly throw somebody in an entirely abstract world of electronics might be a bit fun. So what I thought was, the same stuff that courses through the power that runs our houses, runs our country, is actually has the same trace, if you plot it out, as what a pendulum does if it starts swinging. So we can take something that's quite concrete, quite visible, and we can set it swinging, and we can produce this sine wave. And we can have a student capture that information and then start playing about with the different numbers in here and trying to match up the value that they have extracted from the data and then turned back into a calculation to see if they understand what's going on. And when they've got that, then we can take them into the rest of the stuff we do in electronics. So this bridges them in. And from there, we have lots of other exciting experiments just about to pop through the surface, and I look forward to showing them to you in the future. So with that, I am going to magically go back to the talk and say that you can do real experiments anywhere. And like Nick, I got a bit jealous. I had to connect to my pendulum whilst flying back to New Zealand at Christmas. Thank you very much.
So we're just about at the end. I just want to wind up by pointing out some facts and figures. Lab usage and occupancy. I know that there are people watching this who are very concerned about the university finances, so I want to indicate that we're not breaking the bank just yet. This is how we're using it. We have 17 modules that are already, from entry level to master's level, using resources in the Open STEM labs. We've got, as I think Mark made this point, 50,000 student hours in the lab or observatory or field in 2016. We see that that will grow because we have 20 further modules that are planning to integrate the Open STEM Labs activities in the next 2 to 3 years. So we're away. But what you've seen here is just the tip of the iceberg as far as the project team is concerned. Behind the scenes, we have project managers. We have some software developers that we recruited especially for this task, and they've risen to the challenge. And then down there is a list of names. You might see your own name and you celebrate that. You might not see your name, in which case see me afterwards if you think it should have been there. I apologise. But there are 18 academics and about 15 technical people and some office staff helping. It's a big operation. You're just seeing the front end of it here. But I'm very grateful to all those people who've enabled us to get to this stage and for my colleagues to show off what we've got. Now I'd like to ask Lucian to come and look after this bit. There's some summary points there.
Thank you very much. Let's show our appreciation to Nick and all the panel. Terrific, thought-provoking. Now time for some questions. So please raise your hands. We've also got social media and live streaming, and we'll hear from people from outside this theatre as well. So please indicate where you are, and a mic will come towards you. Please say who you are and where you're from. And keep the questions short so we can pack in as many as we can in the next 10 minutes.
Good evening, everybody. My name is Alan West. I'm formerly director of the Reach Out Lab at Imperial College, but we operate a company called XITech, which supports STEM outreach activity. I'm particularly interested in the first line there, which talks about employability skills for young people in particular, and the need to encourage more students to pursue STEM pathways at all levels. Particularly encouraged to hear that it might be possible for there to be wider access to the STEM labs. I know from my own experience that to scale up our activities, we'd have to have produced very many face-to-face laboratories to hit a relatively small target of students within, say, the London area. But I just wonder how large this particular programme can become, and if the programme does grow, what needs to happen to support the pedagogical approaches for teachers in particular in schools so they can adapt to these new systems. Thank you.
Well, thanks. It's a very interesting point that you make there. I think what we believe that what we want to do is we've got use of this, like any university's got use of its laboratories. And if you go to any university now, you see the lights off in the labs. So we've got this ability to keep the lights on at night and to go on. We've got terrific capacity. But we only need a certain fraction. What we need then is other people to help use it, because I've set the team a challenge. I want the equipment to be absolutely worn out by the time it needs replacing, and it needs to earn its replacement. It can earn its keep in the curriculum. You've seen how much it's being used in our own curriculum, so it'll earn its keep through that. But to go further, then we need ways of using this capacity, and we need to then work with local educators. Well, they don't have to be local. We need to work with other educators who would like access when we're not using it. Our own requirements are a small fraction of the time in some areas, slightly more in others. I mean, I think the telescope's quite heavily used.
Yes, the telescopes, as I was indicating, even though they are still in the final phases of commissioning, are essentially used every clear night, all night long, and produce gigabytes of data night after night. I was also touching upon the plans for telescope.org, which is a subscription service which would be perfectly suitable for schools in particular where it used to be deployed. What we hope to add as a different spin to the way it was done in the past is what we call batched open course, which is a free resource for self-study, introducing the concept of observational astronomy and the telescope and the science that could be learned with it and access via the telescope.org site for the students. And so we would hope to bring this into schools, supported by the many open learn resources we already have on astronomy, to open up interest in STEM via astronomy, which is still very popular, without having to send into each school people to present it over and over again. So we will seed it and then have this self-study resource alongside access to the telescope.
Great. Any more questions?
Shirzadi Materials Engineering. So with 2 telescopes, or let's say 10, 20 rigs, like a pendulum you showed, and thousands of students, so what is the waiting time to access that? I mean, let's say, when you say that amount of student hours access the system, so how many days I should wait to see that pendulum is free at my disposal, and particularly with the telescope?
Yeah, okay, we operate a booking system so that you can plan ahead. We have multi-sets, as you pointed out. I think it's a question of time management and expectation management. Tim, are you frightened by the idea of having 800 students on an electronics course?
Nope. The amount of equipment that we're putting in the lab is designed so that on any given course we can put 1,000 students through the experiment in a weekend. And we're going to give them a 2 to 3 week window per experiment so that they might have, on my second level electronics course, about 8 experiments to get through in the course of 32 weeks. So if I can get the entire course through in one weekend and then they've still got 2 3/4 weeks left to get through it, they can have another go. So capacity is absolutely not an issue with the engineering side, because there will be so much equipment in there that will have plenty of capacity to handle those sorts of numbers.
Mark, do you want to say anything about the possibility of interactive screen experiments to prepare for labs?
I mean, that's the one thing. I mean, the scalability for the on-screen experiments to actually give students a chance to develop their skills before going to a live instrument is actually that we handle thousands of students in those modules anyway. So 1,000 students accessing a digital microscope is not a problem whatsoever. But then timetabling them into a live microscope can be more of an issue, but it's about booking, it's about timetabling. And I think the only other thing I'd say is that a lot of the instruments are going to be also used in a team context, so actually where you've got groups of students coming in, which also allows you to scale up as well.
Can I just add, for the purpose of the telescope, because you specifically asked about this as well, the real-time use of the telescope is in small groups and pre-booked, and obviously there is a certain limit of how many students can channel through. This is, however, also the most advanced use. There's a good deal of preparation needed to really understand what it is they are doing and learn from it in a sensible way. So this will be limited, the real-time use will be limited to the more advanced levels of modules with fewer students. The rolling out to the mass market, to many students, is done in the hands-off mode via the the subscription service, where you request a certain observation to be done, which is then queue scheduled and perhaps takes a week to arrive, but then you have it. It is interesting to note that this concept was shown to work perfectly with large numbers of users who typically request very similar observations. So there is a scalability there by pooling requests.
Thank you very much, Ulrich. We've got time for one more question, I'm afraid. If we don't have time for more questions this evening, we will take your questions and the panel will answer them. We've got one more question from that gentleman there. Okay.
My name's John Licknovich. I've worked in the IT industry for about 44 years now. 2 questions, really. One is around the architecture of OpenSTEM. Is it the sort of thing where you could actually incorporate other centres, bring them into the OpenSTEM concept? They could have their own instruments and even have students or smaller groups that were actually providing information into the lab for everybody to use? And the second question is, where are you storing all your data? I mean, it sounds as if there's an awful lot of data around. I'm assuming that we're not back in the old mainframe days, that this is either in the cloud or distributed around. Would you like to just talk a little bit about what's behind this?
The data. Ulrich, do you want to take the
Yeah,
first part of that?
yeah. What was the first part again? I was busy getting rid of the data. Oh, it was the connectivity. No, I've got it. I've got
other
it.
people working with us, other instruments.
Yes, of course you can. The thing I'm actually working on a little demonstration of that in my garden shed right now. And the important thing about the architecture behind the way the engineering lab side works is that the video leaves the equipment and goes directly to the student or the user, whoever they are. It doesn't come through my lab. All that my lab does is it arranges the conversation. So that means that if somebody wants to arrange a conversation where they're in Antarctica and the other person's in the Saharan desert, it's absolutely fine. All they need is for the internet packets to go between those two extremes and we won't see them. So my service can help out anybody anywhere.
So we believe there's hope. Ulrich, you're a
In
big
terms
data
of
generator.
Data, yeah, it is quite correct. Astrophysics is very data intensive, and should I say this is also addressing employability, because our students will be experts in data mining and using large data archives and having a feel for how this is done. In practice, how this works for us, as I was saying, we collect many gigabytes of data every night. They go into the cloud to begin with and are there for student use to access for a certain time, but then for permanent storage, currently there's a data archive on campus. Data disks aren't, luckily at this point, not that expensive, so for now we are okay. In a few years' time, we may need to reconsider how we store this forever.
We're going to put it in Tim's shed, actually.
Remember that, Tim's shed. Elaine Murphy, my colleague, we have a question from live streaming, do we?
Yeah, we have a few questions, but I'm just going to pick one. It's about accessibility. Do you think the it's from Jo Buxton. She hasn't said where she's from, but do you think Open STEM Labs is making these services more accessible for disabled students, and are you tracking this?
We're very concerned about it because it's part of what we do. Inclusivity is a big issue. I believe that it is more accessible from the point of view of you don't have to do the travelling. I mean, you can do this from where you are able to get, where your choice of study location is. So from that point of view, we're able to take people to places that they wouldn't otherwise easily have been able to get, whatever issues they have. I mean, for all of us, I can get to a telescope without having to go to Tenerife now.
Thank you very much, Nick. To close this wonderful evening, we'd like to hear now from Professor Simon Kelly, who's the Interim Executive Dean for STEM, of course, our largest faculty. Over to you, Simon.
Thanks, Lucian. Wow. Fantastic talk, guys. The Open STEMs labs are a fantastic space for practical learning. They're about scholarship and practical learning. It's an opportunity for students to use real professional research-grade kit to be tutored by our academics. It's a vehicle for collaborative learning, and it's about teaching collaborations. It does so many things. It's a really amazing thing. Thanks once again to all of our speakers. Thanks to all of the Open STEM team whose names did appear and didn't appear on the screen. We'd like your feedback on the event, so we're grateful I hope you've got forms. We'd be grateful if you have a chance to fill out those forms and give them to staff as you leave. This is just one of the topics that the OU engages in. We've more planned in the next academic year. From our key research areas, we're going to hear from education, international development and citizenship and governance, and there'll be more from space science coming up as well. If you want to find out more about opportunities to study STEM courses, there are some relevant courses listed on the Open STEM Labs website. You've heard references to the MSc in Space Science and Technology tonight. This course begins this month, but don't worry, it'll be running again in a year. The course will equip students with the skills to run major space missions. In fact, they'll be working on some live missions during the course, and it's suitable for those with an academic or professional interest in the subject next year. There's more time now to chat informally if you want to below. There'll be some drinks available. So please join us in the foyer and take a look at some more of the STEM labs. Thank you.